Hello everyone, so today I'll be presenting a paper titled Self-Supervised Graph Representation Learning for Black Market Account Detection. This paper was published at WSDM 2023 by researchers from Xiamen University and Tencent. So WeChat is a popular super app in China. It has over a billion users and it supports messaging, payments, and even login to third-party apps. But unfortunately, its popularity also attracts cyber criminals. So MMMA is a multi-purpose messaging mobile app, such as WeChat, and BMAs are black market accounts. They are accounts that enable fraud by selling access, but these accounts are actually not directly involved in fraud itself. And these accounts are actually hard to detect because of privacy concerns of law, and that makes the accounts have lack of labels and generalization challenges and high user behavior diversity. So the big question is, how can we effectively detect BMAs in such a massive environment? So in this paper, the authors are using a graph-based account detection, which treats accounts as nodes and interactions as edges. And the GNNs have shown success actually, but they usually need a lot of labels. And because for this dataset they don't have as much labels, they will be using self-supervised learning. So the key challenges are there are three in this paper, which is firstly the user data is huge and very diverse, making rule-based systems very ineffective. And then new accounts are also are created every day, so that the system must generalize well to unseen data. And then thirdly, WeChat cannot access private user content due to privacy laws, so labels are extremely limited. And to address these problems, the authors propose a system called SGRL, which is self-supervised graph representation learning. It uses GNN and self-supervised learning to generate useful representations of accounts without relying on large labeled datasets. And the system is operated in two phases, which is pre-training, which is where representations are learned using structure and attributes, and a lightweight detection phase, where suspicious scores are computed online for new users. So here is the main architecture of the SGRL itself. There are four main components, which are the IG encoder, the triple S encoder, double S encoder, and then the SSA encoder. The IG encoder is an inductive GNN that learns to represent nodes using only their attributes and local structure. And then the triple S encoder is a self-supervised structural encoder that uses contrastive learning between a node and its local subgraph. This helps capture patterns without using labels. The double S encoder is a supervised version that uses a few human-labeled BMAs and non-BMAs to guide representation learning. And then the SSA encoder is a self-supervised attribute encoder that learns which node attributes are most correlated with being a BMA. So contrastive learning approach, the main idea is that they want to maximize the mutual information between the node and its subgraphs and the node and the attributes and pseudo labels. So it will give a positive and negative scores. For example, for a node and its subgraph, it will give a positive score. Whereas if a node and is connected to a subgraph from another node, it will give a negative node. And this works usually because of how BMAs often have suspicious like structures. They have these like connections with other nodes, and then it will also use k-hop neighbors as subgraphs. So here are the experiment results. The SGRL are found to outperform other methods. So in an offline experiment on a million scale WeChat graph with 100,000 labeled nodes, it achieved a score which outperforms the strong baselines like GCN, GAT, and Deep Graph Infomax by significant margins, up to 20% in an F1 score. And SGRL was also deployed in a real-world WeChat environment. In the online test, it processed a billion scale graph and improved the detection success rate by 7.27% over the best baseline. These results show that the model is not only accurate but also scalable. So key conclusions for this paper is that it presents a novel self-supervised framework that tackles the black market account detection problem using a graph-based approach, and by combining contrastive learning on local structures with self-supervised attribute prediction, the authors design a model that requires minimal labeling yet performs strongly in both offline and online settings. And SGRL is currently deployed on WeChat, and it has helped detect hundreds of thousands of fraudulent support accounts for now. So here are the paper strengths itself, right? For this paper, it's very impressive in multiple ways. It introduces a technically sound and novel architecture that blends several self-supervised modules in a way that was well tailored for black market account detection. What makes this paper's results especially notable is that the industrial deployment in WeChat, it shows that this paper is more than just a theoretical model. The impact could be large, especially in pushing forward self-supervised graph learning for fraud or anomaly detection. And then for the improvements for the paper itself, I think the paper very relies on handcrafted attributes, and lack of attention mechanisms could limit its flexibility. Uh, there are very many opportunities that I think can be used, especially applying this framework to their richer graph types like heterogeneous or dynamic graphs might be more better. And so here are finally three questions to finish today's presentation. How would SGRL perform on heterogeneous graphs? How sensitive is the model to the quality of the human design node attributes? And could SSA encoder be adapted to work with automatically instructed features, like from user behavior logs or embedding spaces? That's all for my presentation today, so thank you.
Hi everyone, today I'm going to talk about GEO, Generative Engine Optimization. I'm Ninja Hui, and this is paper presentation for Dynamite. So, what is Generative Engine? Generative Engine is a combination of conventional search engines with generative models. It's able to search for information and generate multimodal responses by using multiple sources. Formally, we can describe a generative engine as a function. First, the user gives the query to the model. Then this query model will reformulate the queries which gets as Q1. Then these reformulated queries will be given to the search engine to get the search results. The results will then be summarized with GSUM and will be combined to make a response with the response model. And the response is supported by a set of citation. And to ensure factual accuracy, a high-quality GE must achieve higher citation recall. This means that the responses are supported by relevant citations and maintain high citation precision, which means all citations accurately support the statements they are associated with. The problem comes from the nature of GE. It's great for users, but they pose a problem for website owners and content creators. In traditional search, feasibility is tied to ranking, but in GEs, content may be quoted, paraphrased, or summarized, often without clear attribution or feasibility. This means high-quality content might contribute to an answer, yet it receives no clicks, no traffic, and no recognition. To address this problem, the paper proposes Generative Engine Optimization, GEO. This is the first novel paradigm to aid content creators in improving their content feasibility in generative engine responses through a flexible black box optimization framework. GEO's black box optimization framework will enable the website owner, which lacked feasibility originally, to optimize their website to increase feasibility under generative engines. And this general framework allows content creators to define and optimize their custom feasibility metrics, giving them better control in this new emerging system. In traditional search engine, feasibility is based on ranking. Higher position means more feasibility. In generative engines, feasibility is more complex. Responses are structured blocks of text. Citations are often embedded within a sentence. A website may appear without a clickable link. Thus, new feasibility metrics are required. The paper proposes a position-adjusted count that reduces the weight by an exponentially decaying function of the citation position. Intuitively, sentences that appear first in the response are more likely to be read, and the exponent term in definition IMP-PWC gives higher weightage to such citation. Thus, a website cited at the top may have higher impression despite having a lower word count than a website cited in the middle or end of the response. You can see that IMP-PWC is the feasibility function of a website, and CI is citation, R is response, FCI is set of set of sentences in response, and S is the number of words in sentence. Well, given this is very good for objective and well-grounded metrics, but this ignores the subjective aspects of the impact of citation on the user's attention. To address this, we propose the subjective impression metric, which incorporates facets such as the relevance of the cited material to the user query, influence of the citation, uniqueness of the material presented by a citation, subjective position, subjective count, probability of taking the citation, and diversity in the material presented. Next part is the generative engine optimization methods for the websites. So basically, they modified the content of the websites by prompting LLM according to a specific style or content changes. These styles are observative, statistic addition, keyword stuffing, site sources, and quotation addition, easy to understand, fluency optimization, unique words, and technical terms. And then, since there is currently no public data set specifically designed for generative engine queries, they created a GeoBench, a comprehensive benchmark of 10,000 queries, which comes from real-world sources and repurposed for generative engines. These sources are from MS Marco, Orcas 1, Natural Questions, All Souls, LIMA, DaVinci Debate, Perplexity AI Discover, ELI5, and GPT-4 generated queries. For the evaluation metrics, here are the more complete list of it. There is position adjusted word count, subjective impression, and then all of those are the members of subjective impression. Here is the experiment result. As you can see, the above one optimization is the baseline. And then you can see the best method is the site sources, which improve on baseline by 41% and 28% on position adjusted word count and subjective impression respectively. And on the left side, this is for domain-specific generative engine optimization. As you can see, for different domain or different subject, the method that excels also differs. And here on the right side is the optimization of multiple websites, which means geo is done to the whole list of sources. You can see that for rank 5, for sources that ranks 5th, it really pushed them and improved their visibility, especially in this for the site source method, which improves their 5th rank by 150.1. Here, on the left side is the combination of used strategies result. We can see that by combining statistics and fluency, we can obtain the highest improvement. And on the right side, we can see several examples of geo method. Here are the experiments result with a deployed generative engine. We can see that with the proposed method, both evaluation metrics improve. So, what are the limitations? There's 3 limitations that is clear. First one is the adaptability over time. The proposed methods are methods on current generative engines, but as these engines evolve, similar to how SEO has, geo strategies may require frequent adaptation to remain effective. Query drift. Although GeoBench is carefully curated, the nature and distribution of user queries may shift over time, highlighting the need for continuous dataset updates to maintain relevance. And third one is the limited evaluation of search engine interaction. The paper does not directly evaluate how geo-modified content influences traditional search engine rankings, which may still impact visibility. And here are the 3 questions that I would like to ask the author. How do you envision geo methods evolving as generative engines become more complex or start ingesting larger contexts? The next one is, do you have plans to release periodic updates to GeoBench to reflect evolving query patterns and ensure continued benchmarking accuracy? The third one is, could you elaborate on how you plan to assess or mitigate the unintended effects of geo methods on traditional search engine rankings in future work? And that's all for my presentation. Thank you.
Hello everyone, my name is Nico. Today I'll be presenting the paper Inferring Visualization Intent from Conversation, published at CIKM 2024. The scope of this paper is at the intersection of natural language processing and data visualization, where its main topic is on discussing how can we help users create visualization through natural conversation. The author introduced Luna, a framework that significantly outperforms existing approaches including GPT-4. The key insight driving this work is that visual data analysis is inherently iterative. Think about how a data journalist actually works. They do not know all their questions in advance. Instead, each visualization they create leads to a new questions and deeper exploration. The authors illustrate this with a real scenario of investigating police misconduct data. A journalist might start by asking, where do the cases happen? And receive a bar chart showing distribution across various cities. Seeing the results, they might then ask how do cases change over years to get a time series chart. Based on that insight, they might also continue with a question, what about cases after 2016? Each question building on previous findings. So the solution here is using natural language as the interface for this exploration, making data analysis accessible to people without programming skills. So why is this problem so challenging? The authors identify 3 critical issues with existing approaches that make them unsuitable for real conversational visualization. First, generating executable results. When you use end-to-end generative models like Picard, they often produce SQL queries that simply don't run. The authors found that Picard fails to generate executable queries 40% of the time. These failures include syntax error like incorrect quotation marks or semantic errors like trying to average text columns. Second, handling language ambiguity. When someone says, "What about those cases after 2016?" what cases are they referring to? A human will understand that they mean the weapon-related cases from the previous questions. But rule-based systems like Picard require exact matches to column names and can't handle these implicit references. Third, managing conversational context. The current questions almost always depends on previous questions and results, but concatenating all previous contexts, as Picard does, makes it very hard for models to correctly understand these relationships. So the result for the current models are not great. GPT-4 achieves only 44.87% accuracy and Picard's perform 50.14% accuracy. To solve the problem discussed before, the authors propose Luna, a framework that takes a fundamentally different approach using a divide and conquer strategy. Luna's key innovation is recognizing that this complex problem can be broken down into much simpler, manageable subproblems. Instead of trying to generate everything end-to-end like previous approaches, Luna decomposes visualization intent into its core components. The insight is that visualization intent consists of two main parts: the attributes you want to visualize, like showing the distribution of weapon found cases, and the filters that determine which subset of data to include. Luna systematically breaks this down into six specialized subtasks. First, predict how many attributes to visualize, then select which specific attributes. Next, predict how many filters to apply, then select which attributes to filter on. Finally, for each filter, predict the operator and the specific value. So, why does this work so much better? Luna guarantees that it is always executable results because you are selecting from valid options rather than generating free text. Each subtext is much simpler to learn than the full problem. Now let's look at Luna technical architecture, which consists of 4 different parts. First, the foundation. They use fine-tuned BERT-based model with only 110 million parameters. And next is the input format. Instead of concatenating all previous conversation results like other approaches do, Luna creates a compact summary of previous intent. This format is very intuitive because it directly tells the model what was previously visualized and filtered, making it much easier to understand the current request in the context. For the specialized model, they use 3 different architectures optimized for each task. Classification heads works well for counting how many attributes or filters to use. Attention mechanism excel at selecting which specific attributes are most relevant to the user's query. And for filter values, they found that simple rule-based text matching actually works better than complex neural approaches. For context handling, using the right tool for each subtext rather than forcing everything through the same architecture is the key reason for Luna's success. The results are as follows. Luna achieves 57.31% accuracy on the test set, which represents substantial improvement over all the baselines model. Luna is also more efficient. It uses only 12% of the memory required by Picard-3B and runs inference in only 0.1 seconds, compared to Picard's 152.6 seconds, which is almost 1,000 times faster. For practical applications, Luna always produces executable results, comparing to Picard, which fails to generate valid SQL 40% of the time, making it essentially unusable in real applications. Conclusion: Luna is the first systematic approach to conversational visualization intent. Luna achieved 14.3% improvement over the state of the art. And Luna solved the fundamental reliability problem compared to the other generative approaches by always producing executable results. But there are some limitations. The evaluation dataset is derived from SQL conversation and not visualization scenarios. The scope is quite limited, only 4 filters operations and 19 categories, which real visualization needs are much more diverse. And the solution is incomplete. The current framework doesn't address visualization type selection, which is crucial for practical deployment. Finally, these are the 3 questions. For context window management, how does Luna handle conversation that exceeds BERT's context limitation, and have the author considered more recent architecture that could capture long-term conversational dependencies? The next questions, the author evaluation assumes user will correct wrong intents before proceeding. But how would Luna handle cases where users accept incorrect visualization and continue the conversation based on the flawed results? The third question, Luna focus on intent inference but doesn't address visualization type recommendation. So how do the author envision integrating automatic chart type selections, and wouldn't this significantly impact the practical utility of conversational visualization systems? And that's all for my presentation. Thank you.